Then we come to the second talk, MRI and cortical thickness. What does it mean? Alan Evans from the McConnell Brain Imaging Center, Montreal, and McGill University, Montreal. Please, Alan.
Good morning, everybody. It's a pleasure to always to spend time with Carl, and I think that Carl gave me this title more or less to be provocative, as he always is, because Carl has for a long time been somewhat skeptical about cortical thickness based on MRI. And usually this is Carl's position. You cannot measure cortical thickness properly using MRI because of the poor resolution. And my usual response is that's the same as saying bold is useless because it's not really blood flow. Both positions are correct. It's very difficult to extract microstructural anatomy from 1 millimeter resolution MRI. But at the same time, heuristically, it's used in lots of different practical applications. I'm going to try and cover mostly methodological issues. I'll give you a little bit of history before we get to that. It is, of course, true that high-resolution data, post-mortem data, is very high resolution. It affords us the opportunity to look at multiple stains, to look at the microstructure of cortex. But the low-resolution MRI has its own advantages. It's in vivo, it's non-invasive, it's inherently 3D, and one can do longitudinal studies with it. So these are the trade-offs of these two universes. So this is what we're talking about, extracting the exterior and the interior surfaces of the gray matter mantle to extract morphological information from these. When I did a preparation for this, I did a search and looked at the dramatic increase in cortical thickness-based publications of all stripes. And if you do a brain spell search on cortical thickness, you find something like over 10,000 applications in various areas using cortical thickness. So it's obviously very attractive to a lot of people. I'm just going to briefly run through, just show you some snapshots of typical applications. Don't dwell on these. We're going to talk mostly about methods. People have looked at age, changes in cortical thickness, in the full lifespan or during development. People have looked at for instance, regressing hormonal levels, looking at gender differences on cortical thickness evolution, or any number of behavioral indices against cortical thickness. All of these have been done in normal development. One can look at any number of diseases. In this case, Philip Shaw's work at St. Louis, in NIH, looking at delayed maturation of the frontal cortex in ADHD. I always like this data set because it shows a delayed maturation in frontal cortex, which would be consistent with the suppression of inappropriate responses and the clinical presentation in ADHD. And there's one region where the cortical thickness was actually exaggerated and increased in that disorder, in the motor strip, which all gives us some confidence that it's telling us something. A number of people have explored the genetics of cortical thickness. Again, I'm not expecting you to read these, just get a flavor of the wide range of applications that have made use of the cortical thickness methodology. Now, historically, there are quite a few groups who started in the late 80s, mid 90s, just a few snapshots of some of the groups. David Van Essen's group developing the CARET software, Rainer Goebbels' group developing Brain Voyager, and Jean-François Mangin developing Brain Visa. Now, this early work was largely oriented towards surface extraction per se, modeling of the gray matter cortex to understand sulcal folding patterns in brain. At about the same time, Anders Dale and Bruce Fischel and colleagues were developing the free surfer package, originally in San Diego and then Boston. They did a lot of work in terms of extracting the inner and outer mantle surfaces of the cortical mantle and also did in the mid-2000s some very nice work to explore the stability of MRI-derived measurements of cortical thickness against scanner features of strength, upgrade, version, manufacturer, and so on. In parallel, my group in Montreal was developing the same package. It was originally called ASP, and it was developed further with constrained Laplacian constraints to be called CLASP, which was then incorporated into a fully automated pipeline known as CIVET. These are all there for you to read at your leisure in the write-up. And over the last 10 years or so, there's been an absolute explosion of surface-based methods, voxel-based methods, and tools to start understanding and comparing these various methods. I can't hope to cover the entire waterfront in this talk, but those are the references for you. So what are we trying to understand? We're trying to understand cortical anatomy. We're trying to understand this beast, the laminar structure of the cortex from layer 1 at the peel surface down to layer 6 at the gray-white interface. The gray level index was originally conceived by Axel Schleicher with Carl and Katrin to define cortical boundaries that might change their profile as one moved from one cyto-architectonic area into another. And we're trying to capture this kind of information, these boundaries, using data which is typically collected at 1 millimeter, which is not easy. We can't tell what is giving rise to the changes in the surface boundaries. Changes might be due to reduced size of neuronal cell bodies, a smaller number of neuronal cells, or increased myelination. All we can see is contrast. However, having said that, there have been some validation studies that have looked at the correspondence between the MRI-based approaches and direct anatomy. Fischl and Dale in 2000 showed a distribution of cortical thickness which was on the order of 1.5 to 4 millimeters, which is consistent with what we know anatomically. They showed the posterior bank and the anterior bank of the central sulcus, as measured by the automated surface extraction, were consistent with results obtained by manual microscopic assessment in individuals. Cabani, in our lab in 2001, did a manual analysis to compare across 20 brain regions in 40 brains, looked at the correspondence between the ASP extraction of cortical thickness and showed pretty good correspondence over only 4 regions out of 20 showed a significant difference between manual and automated methods. Now, if we come to the methods, I could not possibly cover all of these. I just apologize to the authors of these methods, but I put them up there for your subsequent perusal to explore these different methodologies which have come into play. But they all start out life as requiring segmentation into gray matter, white matter, and CSF. This is the first step for all methods. And the methods subsequently split into 2 classes: voxel-based, which do not require an explicit modeling of a cortical surface. One of the earliest examples of this approach was by Jones in 2000, and essentially they're looking at solving the Laplace equation from the white matter boundary to the gray matter boundary of the peel surface, solving Laplace's equation to integrate the vector field across the scalar field from gray matter to CSF. So this gives us a one-to-one mapping from inner to outer surface and a measure of cortical thickness at each location. Hutton in 2008 with some early work in 2002, extended this basic approach to allow extraction of streamlines over sub-layers within cortex. They found typically measures of cortical thickness which were, again, consistent with the anatomical measures, peaking around 2.5 millimeters. Hutton went on to compare then cortical thickness, voxel-based cortical thickness analysis with the more well-known voxel-based morphometry within the same pipeline environment. And the results are shown here, and it shows quite consistently that whether it's vertical cortical thickness-based or volume-based, a decline in gray matter volume or cortical thickness as a function of age, a difference between males and females here, which is essentially being driven by the difference in cortical surface area, because the cortical thickness is the same for males and females. And when she compared voxel-based morphometry and voxel-based cortical thickness analysis, the conclusion was that VBCT and VBM yield very consistent results, but the cortical thickness approach provides a more sensitive measure of age-assisted decline in gray matter compared with VBM. The findings suggest that cortical thickness selectively investigates cortical thickness, whereas VBM provides a mixed measure of gray matter, including cortical surface area and cortical folding, as well as cortical thickness. So cortical thickness provides a more definable biological metric that can be quantified, rather than a sump parameter which combines multiple different biologically independent variables. Scott, in 2009, also applied a voxel-based approach. He used a canny operator. For those Brits in the audience, I always wanted to say canny operator. This is much the same general schema as Jones and Hutton, and they came up with a validation scheme which showed pretty reasonable results in comparing their measures of cortical thickness with a variety of manual and automated validation studies, all presented here. And they showed pretty good concordance between their voxel-based extraction methodology and the validation measurements. If we move on to the other strategy, surface-based approaches, they generally require extraction of the tissue classification, as I said before, but you have to first of all deal with the potential bias of field inhomogeneity. White matter extraction, evolution out to the gray matter surface to provide cortical thickness, and then usually some smoothing component to regularize and Gaussianize the distribution of cortical thickness measurements. So generally, we're extracting cortical thickness at the gray matter, white matter boundary, and then evolving that out to the gray matter surface, as shown visually below. The civet approach is using a constrained Laplacian approach to similar in spirit to the Jones Laplacian approach in the voxel space, but this is not being applied in the surface space to evolve the surface from the white matter surface to reach a skeletonized version of CSF. The skeletonizing overcomes the partial volume problem, which I'll explain a little further in a moment. The cortical thickness analysis. Now we've extracted the two cortical surfaces I just showed you. There are a variety of different metrics which can allow us to measure the distance between these surfaces, from simple coupled surface linked points on both surfaces. This is what is typically used in civet. There are more sophisticated strategies to look at the closest point, dropping a normal from the inner to the outer surface, or a Laplacian approach heat flow, as I've described. The largest enclosed sphere rolling a ball around the inner surface, and a minimum line integral. Any number of these different metrics can be used to give us a measure of the cortical thickness. Now, one of the issues that attends this problem is the issue of spherical topology versus geometric accuracy. In an ideal world, you want to maintain spherical topology so that one can establish a one-to-one correspondence between cortical thickness measurements in different brains. The problem is that sometimes getting into the deep crevices is a very hard sell for the evolving, deforming surface. And Fischl notes that it's often better to accept some topological defects so as to get a better fit of the deep crevices. And this might introduce handles and holes in the surface, and those have to be dealt with subsequently. To the extent that you do have one-to-one correspondence across subjects, it is possible to integrate iteratively across individuals to, in this case, in this example, increase the overlap of sulcal folds and gyri. This shows in an example from 300 subjects the improving alignment of sulcal gyri and fundi. This shows the corresponding reduction in standard deviation of corresponding points across these 300 subjects. So life gets better and better as the surfaces are aligned in this iterative fashion, taking advantage of the point correspondence. And this allows us to, for instance, generate average surfaces which give us a very nice representation of average surface folding patterns, and in this case, the difference between the mean left hemispheric surface and mean right hemispheric surface. One of the big issues that comes up a lot in cortical thickness analysis is the question of longitudinal analysis. If you have individual subjects who are scanned multiple times, one wants to take advantage of the fact that those brains should be pretty similar as a function of age. You don't want to throw out all the baby with the bathwater, but you want to keep some of that information to take advantage of within subject consistency. There are many papers which have addressed the longitudinal analysis question. One that was recently published in 2012 by Reuter et al. Is demonstrated here. You take all the different time points. They are all mapped into a common minimum variance frame, not the baseline, not the first scan, but the composite of all of them. This allows one to take the surface that's extracted from the median of all of them and use that as a constraint on the mapping of any individual time point. If you do that, you get this kind of improvement. This is a map of the percentage change between two time points when one does not take into account individual the longitudinal component of the data within any individual. If you do take account of that longitudinal information, you can reduce the amount of noise in the system dramatically from about 6% here down to about 2% here, with significant changes in consistency across subjects. And this ultimately gives rise to a much greater degree of error reduction. You see the large error bars here on the cross-sectional approach reduced in the longitudinal approach, and this gives a greater discriminating power for group difference. However, this field never stops moving under our feet. Wang in 2013 declared that they'd come up with an approach which was somewhat better than the longitudinal approach I just described. They show a comparison here between the Reuter approach and their own proposed method. This perhaps is misleading because what they've done here is impose constraints on cortical thickness at each time point to introduce a longitudinal constraint, and that can be essentially considered as just interpolating across time. Nevertheless, they've put this forward as a competitive method. I'll briefly go over some of the sources of error that come into play when we're doing cortical thickness analysis: noise, contrast, resolution, and motion. First of all, noise. This is a study that was done in 2004, I believe, no, 2005 by Jason Lurch, looking at 27 different versions of the same brain. There's the average of the Colin brain there from these 27 different images. And one can ask the question, how well can extract that surface? How consistent is it? And you can ask two different questions to how to deal with the noise in the measurements of the same surface 27 times. If you don't smooth the data at all, you can ask, what's the required N to recover a 0.5 millimeter difference between two groups? How many do you need in each of those groups? And without smoothing, you need something like 200 subjects per group. If you smooth the data, you can reduce that dramatically down to very low numbers required to extract a 0.5 millimeter difference. Of course, the price you pay is that this is no longer at a voxel, it's distributed over a region. You can ask the same question in a different manner. If I have 25 subjects per group, what is the largest difference I could actually detect at 0.05? And without smoothing, it's 2 millimeters, which is essentially useless to you. If you smooth the data in the same fashion, you can extract a few tenths of a millimeter, again with the constraint that it's not at an individual vertex, it's over a surface patch. But oftentimes that's perfectly acceptable. Contrast. This is a permanent problem for cortical thickness analysis. You have real biological variation due to cytoarchitecture and myeloarchitectural changes, but you also have machine artifacts due to variable RF penetration, non-uniform coil sensitivity. All these give rise to changes in intensity. For instance, look at the white matter intensity changing from front to back of the brain here. This plays havoc with any attempt to do tissue classification into gray, white, and CSF. Here's the bias field that's extracted by the N3 algorithm. And this is the restoration of uniform density for the three tissue classes that you subsequently wish to segment, gray, white, and CSF. The problem gets worse as you go to higher field. This is the bias field at 1.5 Tesla. This is the bias field at 3 Tesla. You see the profiles there, which is not good for 1.5, and it's really bad for 3 Tesla. So this has to be dealt with before you can do anything. I thought on this schematic it would help make the point about the impact of that bias field on cortical boundaries. If we posit two regions, region A and region B, with different cortical profiles from gray matter down to white matter, you see that the 50% threshold between maximum and minimum intensity gives rise to a boundary for region A, which is here, and a boundary for region B, which is here, further out, because there's a slower roll-off in the intensity profile for region B. If I just add a bias and move region B upward, I'm not moving it out, just moving it up. The consequence for that is that while, of course, there was no bias in region A, but there is an intensity bias added to region B, that shifts the whole region B curve up, and the consequence of using the same threshold is that the edge moves further out. So distortion, bias field tends to shift the boundary forward or backward depending on the nature of the intensity bias. And this can be shown, illustrated in another way. Here, if you look at the intensity threshold and a gradient threshold, basically the gradient threshold shows it's a gradient threshold approach which is more insensitive to a bias field. is mostly red, meaning it's mostly at the point where there is a maximal gradient. This is the surface that would be extracted from that same data set using an intensity threshold. And basically, you've shifted always away from the maximum gradient point using the intensity threshold. And this is essentially being driven by the bias field. You've just heard from David one of the other issues of contrast difference, and this is a real biological bias field. We have areas, for instance, in the precentral gyrus, which have very different amounts of myelin in cortex. So we see differences between this region here and this region here in T1 intensity and in T2 intensity, which can be turned into a ratio. This is work by Matt Glasser and David, which allows us to colorize the myelin content and show us a map of the degree of myelination in different brain regions where you expect to see high levels of white matter infiltration into cortex. Nevertheless, if you're just looking at T1 alone, you will be confounded by these changes in contrast in areas which are different in myelin content. Resolution, otherwise known as partial volume. Here's the problem that if you have voxels which are too small, contrast differences which are too close, you will get bridges from one side of the sulcus to the other. This is particularly bad in pediatric settings where you do not resolve the CSF in that area. This is the same sort of area in an adult, and you see greater degree of CSF extraction. And here we have problems associated with the spatial resolution of the actual imaging device. This is all taken at 7 Tesla, and what you see here are changes in the boundary depending on the voxel size. So the voxel size has a significant impact on the location of the border. And lastly, motion artifacts. If you move, it has major consequences for the apparent cortical thickness. This is work by Reuter in 2015. Dramatic reductions in apparent cortical thickness as a function of simulated motion, which is improved if you do extreme QC. And lastly, I'm going to just briefly step through some of the comparisons that have been done. This work shows that surface-based approaches have a smaller standard deviation than voxel-based approaches. But this projection-based approach, which is a voxel-based approach, claims the opposite. A smaller reduction, a smaller error rate in projection-based thickness. So I'm simply going to rush. I'm simply saying that at the moment the jury is out because two different approaches, one said voxel-based approaches are more accurate, the other one said that surface-based approaches are more accurate. And I'll close with just a recent comparison of two of the more prominent tools which are out there, the Civet and FreeSurfer, which differ on many aspects, which makes it always difficult to compare exactly why they might be different. But the important point to take away is from this analysis, both Civet and FreeSurfer demonstrated high sensitivity to cortical gray matter changes, both cross-sectionally and longitudinally. I'm going to skip covariance and just end on a quick mention that a lot of what we're trying to do right now requires us to validate our results against some unknown ground truth. And the big brain data set that you will hear much more about from Katrin allows us to examine the impact of microstructural changes at the voxel-wise level. So we can use the big brain as a ground truth for a lot of validation studies for cortical thickness analysis. Here's the surface of the big brain at 400 microns. We're pushing it down to about 200 microns, but every time we go down a factor of 2, the volume goes up by a factor of 8. It gets that much harder as you go to resolution below about 200 microns, but we're working on it. So if you take nothing else away from this talk, The white matter, gray matter boundary is determined by cyto architecture. The T1 white matter, gray matter contrast is driven by myeloarchitecture. And we'll still be back here in a year's time. Thank you very much.
Thanks, Alan. Any questions? Then come forward to the micro. Okay, it's up to you to make this course as interactive as you wish. Yep.
Very nice and interesting summary. Is it useful to obtain 2 or 3 identical data sets in a row of a subject to sort of average them and denoise and get some denoising from start instead of doing smoothing later in the study?
I'm sorry, did you say it's better to use multiple scans from a single subject?
Yeah.
Yeah, it's certainly, it's a trade-off. If you can do multiple scans, should you do multiple scans or should you just scan for longer? Of course, if you scan for longer, you have to deal with potential patient or subject motion. There are methods now to overcome that with navigator echoes. So it's probably, if you can, do a longer scan, but if you can't, then multiple scans obviously are better than one scan.
Okay. Thank you. Thanks, Alan.